Good evening, everybody. Thank you. My name is David Darling. I'm the Dean of the School of Engineering and Applied Science here at GW, and I'd like to welcome you this afternoon or this evening. I'm going to keep my opening remarks brief because I don't want to eat into the program, which I think you will find very interesting, quite unique, and certainly educational. I want to thank especially our panelists this evening for contributing their time, especially one or two who've come a fairly significant distance to be here. I'd also like to offer a big thanks to the gentleman on my right here, Professor Philip Bardé, who is the organizer of this event, and he's also going to be the moderator for the panel. I'll just say a word or two about him. He joined us as assistant professor in the Mechanical and Aerospace Engineering Department this past September. He earned his PhD at Berkeley in nuclear engineering about 4 or 5 years ago. 4 years?
I don't know.
It's too long ago. A while ago. But anyway, he's had a postdoctoral experience at Berkeley and also at Caltech, and then he came to us last September. If you've watched cable TV, I think, and read in the print media and listened to our representatives talk about the earthquake, the tsunami, and the ensuing event at the nuclear power site over the past few weeks, I think you will be acutely aware, at least I was, of the difficulties that typical reporters have, I think, on reporting on such events. And if you've listened to the many public figures, I think they have faced the same difficulties as well. And I think many of us, certainly myself, came away from listening to many of the reports quite confused about the sequence of events that actually happened, the danger, the risk, and so forth. So when it comes to, I think, understanding, not elementary, I shouldn't say that, but basic physics, safety issues, and in the street, the average reporter is rather ill-equipped. So I think tonight's event is a really good opportunity for us to hear from people who are cognizant of the facts, who understand the risks, who understand the technology, and understand what is going on. So I'm very much looking forward to hearing the remarks of the panel. I'm going to ask Philippe in one moment to introduce the panel. And I think the way we're going to structure this, and maybe he'll explain it a little bit more, is each of the panelists will get an opportunity to make some remarks with a PowerPoint presentation, and then there's going to be a general Q&A from the audience. So please sit back and enjoy this event. Thank you very much. Philippe?
Thank you. Thank you very much for coming tonight. So we are very, very lucky to have this list of panelists. I'm going to run through their bio very quickly because we were limited on time, and they all have very, very long resumes that will take the whole evening to go through. So the way the session is gonna work, they are each going to give a 15 minutes presentation on a particular topic that is described on the program here. And then as they go, you will see some hosts that will distribute some cards and some pens. So if you want to write some question that then we're going to collect and we're going to ask them at the end of all their presentations, we could ask them some question this way. Okay. So if you want to ask a question, just raise your hand, and some people will give you some cards. So the first panelist we will have tonight is Professor Manzari from GW, who is a professor in civil and environmental engineering. He's an expert in earthquakes and how structures respond to earthquakes. He's the director of the, I forgot the name. Anyway, he got his PhD at UC Berkeley, and he has been at GW since, for the last 10 years, right? 90. And he's an associate editor of the Journal of Engineering Mechanics at the American Society of Civil Engineering and the chair of the Inelastic Behavior Committee at the ASCE as well. So we're very fortunate to have him here, and he's going to give an outstanding presentation. Then we have coming next would be Margaret Harding, who is a retired employee from General Electric, where she worked for more than 30 years. And she has a lot of experience at GE on the safety and licensing of reactors. She's currently the president of her own consulting firm, of the consulting firm she created, excuse me. And she's an expert. She advises the nuclear industry on licensing and security issues. Coming next will be Mr. Yamachika, who is sitting at the end of the table there. Mr. Yamachika started as a professor in nuclear engineering in Japan, and then went on to work for the government, specifically for the Ministry of International Trade and Industry, and also for the Ministry of Foreign Affairs. He has a very long resume, so I cannot go through everything he accomplished in his long career. But he was in Iraq during the first Iran Gulf crisis, on advising on economy there, and he's an expert in energy and on nuclear fuel cycles. And he has been in Washington, D.C. for the last 2 years, being the general manager of the Washington, D.C. office of the Japan Nuclear Energy and Safety Organization. Coming next, we will have Professor Bittner, or Dr. Bittner, who is a professor, an assistant professor at GW in the medical center. She has 17 years of private practice before deciding to go into academia to teach and do some research as well. So she's in the radiology department, and she will talk to us about the effects of radiation on human health. And finally, Professor Michael Podavsky from Rensselaer Polytechnic Institute in Troy, New York, will describe advanced nuclear reactors. Professor Podavsky has a very long career in nuclear engineering, especially in thermal hydraulics. Thermal hydraulics, for those of you that don't know, is the science or the art of cooling the nuclear reactors. So he's going to talk to us about how new types of nuclear reactors are potentially safer than existing one. And he has a long list of interests and activity, especially in multi-phase flow and simulation. So that's all I have to say for the introduction. So please welcome the Professor Manzari that will describe the earthquakes. Thank you very much.
Thank you, Professor Bardet. I would like to briefly talk about this earthquake and the cause of the earthquake. In this earthquake, probably many of you have seen these facts. The earthquake happened on March 11 in about 15 minutes to 3 in the afternoon. And this earthquake actually was, the source of the earthquake was somewhere about 24 kilometers underground. You will see the mechanism of the earthquake later. The area that was affected by this area is quite large, by this earthquake is quite large. Also led to a tsunami, caused waves up to about 24 meters and reached shores as far as Chile. The earthquake, you also have seen that probably news that caused the axis of the Earth to move and the whole island of Japan to have displacement about 2.4 meters. So geographic position of Japan, everybody knows. The only thing that I would like to mention is that the Pacific Ocean and is right next to Japan, and that is actually, we will see later that that's the cause of the earthquake. So this area which was affected by earthquake is a really beautiful area. If you visit Japan, you will see that actually the whole country is really beautiful, but this particular area is really nice. This is a picture of Miyagi Prefecture, which is one of the closest area to the earthquake, the epicenter of the earthquake. The cause of the earthquake is probably many of us already know, is plate tectonics. Basically what it is that you have a number of plates that are on the crust of the earth. They are floating on the mantle, which is a more fluid type material. So these plates on their boundaries cause earthquakes, basically. What they do is that they are moving with respect to each other. They are either converging or diverging, or one of the plates, especially oceanic plates, may be actually going under the other plates. And this creates what we call a subduction zone in the ocean. So one of the, as you can see on this particular slide, these red lines, they are all areas where an oceanic plate actually is in contact with some sort of a land or some sort of a crust that is connected to a land that is not water. The particular area that we are interested is in here, and you will see later that what happened. So when we get closer, so when we get closer to the Japan islands, you will see that in this area is the area where the Pacific Ocean and the Eurasian plates, they are actually converging. So what happens at Pacific Ocean, it undergoes the Eurasian plate, and in that boundary, you will have a lot of accumulation of energy. And if that energy, but basically what it is that this oceanic plate, Pacific region plate, Pacific plate, what it does is it moves with respect to the Eurasian plate with a rate of about 8.3 millimeters per year. So if the deformation or displacement takes place without any obstruction, then everything would be fine. But the fact is that this movement is not without any obstruction. You will, in its way of going under the other plate, it will reach some, it will face some resistance, and that resistance will lead to accumulation of energy. So when we go back, this is basically, you will see a subducting plate going down to another plate. So this is a typical of a subduction zone. To areas around Japan, we have what we call Japan Trench. Japan Trench is here in the boundary between Pacific Ocean and the Eurasian plate. And what you see here is that basically Pacific plate is going under this. And this causes this particular trench that they call Japan Trench. This has been the cause of many earthquakes for Japan. So this is a picture of the subduction zone. This is the crack that is underwater. So this is actually in the ocean. Now, to tell you a little bit about the mechanism of creation of the earthquake, you will see that this subducting plate is moving with respect to an overriding plate. So this is going under, the overriding plate is here. So as they go, gradually the subducting plate or overriding plate, one of them basically, they will reach some sort of obstacle so that there is some material that resists that movement. And then energy gets accumulated there. This area, we call it a stuck area, gradually stops the full movement of the overriding plate. So what you see that gradually that overriding plate starts bulging. So when it starts bulging, well, there is a limit of resistance that red area could provide. If you exceed that resistance, that energy that has been accumulated suddenly gets released. So you will see a situation like this where the plate gets released, and then you will see a slippage or a slide. So then the tsunami waves develop because of the sudden movement. Now, to show this in more probably graphic way, it's good to take a look at this movie. So you will see that again here, this is moving with respect to the overriding plate, and there is a stocking area here. And then you see a sudden release of energy, and then water starts basically creates that energy that's released because of the upward movement of the overriding plate creates the waves that lead to tsunami. So The fault model that they have looked at for this particular event is on an area of about 510 kilometer by 210 kilometer. And the slippage, the largest slippage that took place was in this area. It's about 23 meters. So when this event took place, the overriding plate moved about 30 to 40 meters up. So it created a large motion. So when you look at from the top, relative to the islands of Japan, you will see this is the area where the stuck area was. This is the area which actually the energy got released. So it's quite a large area. So the earthquake, when you look at the earthquake motion, the ground motion that was measured in Miyagi Prefecture, which is about 70 to 100 kilometers from the epicenter of the earthquake, you will see that the reason this earthquake is so significant is because it consists of actually two very large motions. When you look at the top graph, the top time history, you will see that the top time history shows an acceleration of about 2.7 g. So 2.7 g, we have never had an earthquake acceleration of this amount measured anywhere. We cannot locate that. So 2.7 g in one direction. And you see even the other directions, if you look at the other direction, they are not small. They're significant. So, and the fact is that they are basically two earthquakes coming with this time distance about 60 seconds. So that's why the effect of that is huge. The magnitude of energy that was released is about 2 times 10 to the 17 joules, which is nearly double of what happened in the 9.1 earthquake that shook the Indian Ocean area, the Sumatra. So the energy, surface energy that was released is actually larger. What we call moment magnitude, the seismic moment, which is a total energy, that is 200 times that surface energy. So if this energy, the surface energy, is harnessed, it is large enough to be able to actually power the city of Los Angeles for a year. So, and you know, the amount of energy is something around 600 million times the energy of Hiroshima bomb. This is seismic intensity of the earthquake. So because the earthquake took place in this particular area, you see that, of course, these areas are affected more. These are the areas where, you know, the power plants are, or wherever the buildings are, you know, they got really destroyed. Now, if you look at this is GPS displacement that were measured, GIA of Japan measured them. You see that the lateral displacements is up to, the lateral displacements are about 4-point-some meters. So that means this island moved 4.2, 4.3 meters in this direction. In the direction, because remember, the Pacific Ocean was going down, was subducting, and this was the overriding plate. So after this event took place, this slippage took place, the overriding plate moved 4.2 meters. Now you see also the vertical displacement. Vertical displacement at the island itself is not significant. It's less than a meter. But as I said, right in the ocean, we have 30 to 40 meters of displacement. Now, to put this in perspective as far as the other earthquakes that's in the area, you will see that this Japanese earthquake here is in order of about 9.0. The largest earthquakes in history that was recorded was Chile earthquake that is a little bit larger than 9.5 in magnitude. I want to just mention that all of them that are greater than 9 are all subducting zone type of earthquakes. Now, let me just quickly tell you that the nuclear power plant of Fukushima, this is a picture of that in 1971. It is actually about 40 miles away from the epicenter of the earthquake. And this is the picture of this plant in 2011, right after the earthquake. And what you will see is, I'm going to just tell you that this was designed very well, actually. This was designed and constructed by Kojima Construction, the structural part of it. And they designed it for a magnitude of about 7. But later on, they actually went on. I'm going to just bypass this quickly because this will be discussed later on. This was actually analyzed. What they did was they took this plant and they did what we call a forced vibration test 3 years after this plant was constructed. And they found out that the first period of this earthquake is 0.25 seconds. Okay, if this 0.25 seconds, look what happens. Well, they also then later on went and did an analysis of this using a relatively simple model of this structure. And they found out that the earthquake that happened in 1970 could be very well predicted with the model they had. But the point that we have to bring up here is that if you look at the earthquake record I just showed you, and you plot the distribution of the energy of the earthquake with respect to different frequencies that are possible, you see that the largest, largest magnitude of the energy is actually around 0.24 seconds. The fundamental frequency of this building is 0.25 seconds. This really came so close. So actually, it resonated with the building. So the fundamental energy of this particular earthquake. So yet, this actually did very well. I'm going to bypass the rest of them. I just wanted to tell you this is a beautiful country, and many of us actually feel the same way as these school children in Ahmedabad in India felt right after the earthquake. And thank you very much for your attention.
Thank you. So next we'll have Margaret Harding from for Factor Consulting.
Okay. So I'm going to talk a little bit about the design, the Mark I containment that is common to all 4 units there on the site, Fukushima 1 through Fukushima 4, units 1 through 4. So we're going to just go over it. So when you hear all these terms, it's very hard to picture sometimes what we're really talking about. So my job is to help you get all of that in your head as then we talk about the event and its effect. You're going to see this slide, I think, from all of us. This is a picture of the site. All of you know units 1 through 4 are lined up there on the left, and then units 5 and 6 sit slightly apart from the other 2 units and a little bit further up a hill. Just to understand what you're looking at, the water flow that you see here and here is the outflow from the cooling of the units. So when they talk about the outflow, that's what they're talking about, is that spot right there. And the intake for the units is in this little protected area. So start there. So we start with our geography lesson of the site there. The 4 units we're going to talk most about, Unit 1 was built in 1971. It was a slightly smaller unit. It's considered a BWR3. We're a little arbitrary on the numbering of the BWR designs before about the mid-70s. The very last design that was built in this country was the BWR6. And it's a very specific design that's fairly consistent. But prior to that, GE didn't really number them and somewhat arbitrarily picked when a unit became a BWR3 versus a 4. You may know that most units are quite unique. Each one is slightly different. But these have some similar effects. Unit 1 is slightly smaller. It's a BWR3. Units 2, 3, and 4 are a little bit bigger, a little bit later design, and they're considered BWR4s. So here's just a schematic of the plant to help you sort of, again, get the structure down. There was this reactor service floor, which is this top floor, and then that sort of lightweight structure over the top of it, mostly protecting it from the elements. This is where, when they're doing refueling, this is where the workers are. They're standing up on this area. This is the spent fuel pool that we've heard so much about in this, but normally the fuel sits at the very bottom of it. It has no drain in it, so when people call it a swimming pool, that's an accurate way to think about looking at it, but it does not have that drain in the bottom. That's one of those things you don't really out, so you don't put drains in a tub that you don't want to get empty. So there are no drains in this tub. So then we'll work our way down. This outer structure that's concrete reinforced is sometimes called the secondary containment or the reactor building. It's a sturdy, but that lower part of the building remained very sound. Let's go into the center. This little thing, about 15 or 16 feet in diameter. So it looks small here. It's actually a pretty good sized, and it's 6-inch thick steel. It varies a little bit on which area of it is what. The reactor core sits in the bottom third to half of that. It's typically about 12 or so feet in diameter and about 12.5 feet tall. It's roughly a right cylinder, kind of squarish. Fuel is in these, they're basically really high-tech cans. We'll call them fuel rods. But what it is, a tube of zircaloy. It's about 14 feet tall. It has about 12.5 feet of in it, uranium dioxide. They're arranged in squares that are about 6 inches square or so, and they have a box around the outside of them we call a channel. All of that fancy stuff is to get the water to flow the way you want it to. But this tube, these pellets, is called a fuel rod, but it's really just a very high-tech can. It's welded at the So and it's this very specific geometry, and that's what this represents here with the, wrong thing, little lines here. This outer piece, there's actually a lot of hardware inside that reactor. We call it a reactor pressure vessel. People kind of think of it as this big, kind of egg-shaped thing that's empty. It's actually got a lot of other hardware going on inside of it so that the water flows the directions we want it to. Multi-phase flow is a fairly complicated thing here, and we want that water to go where we want, because in a BWR, the bubbles actually occur in. So you want to make sure the water's flowing the way you want and the bubbles are going where you want. So then this outer red outline is the containment, and there's two parts to the containment. This big outer kind of light bulb shaped official documentation describes it the way GE would always describe that shape. That's a light bulb. It's an upside down one, but it's a light bulb. And it has the connectors to these two round, they look round here. It's actually kind of a donut that sits around the bottom of the light bulb. It's called the torus because of its shape, or it can be called the wet well because you have it about half full of water. Sometimes it's called. The purpose for that piece is that when you vent steam, it'll condense that steam out, free-flowing steam. Heard about that during the accident. We'll hear more about that, I'm sure, in the description. As you drive that steam, condense it, and that does a number of good things for controlling an event that goes on inside these reactors. So that's why this is a suppression chamber. So enough is because the reactor, and that's because it reactor eliminates a steam. It goes through a process that basically, and it sends steam down what's called a main steam line. And basically, so what this is a really high-tech. Okay, boils water, turbine, makes electricity. But what happens is a feed pieces and parts that we left out of this diagram just because it would take me hours and you'd all be bored to tears. A sense of the reactor. But to give you a little sense of actual construction, I believe this is actually Fukushima 1. It would be a Mark 1 world. We built these in Switzerland, we've built them in the United States. Look like this as they were scale, that's a person. 6 foot tall. That gives you a sense for just how big that piece of equipment is. So here's the light bulb. And then you can see all these little connecting pipes, the steam and the various you want them to go. This thing up here is the lid. picture, there's that you got to have. Refueling, which is what Unit 4 was at, of water that sits here, and you put top of the pressure radioactive, you don't really want them sitting in the open. So they all pool off to one side and you're due during an outage. So that gives you, here's a cutaway so that again you can see how it all kind of way to visualize. Painted the outside pretty. This is the, again, this is the reactor pressure vessel right in the middle. Pumps and some of the other things that you need to really run the plant. Dump the steam in, quench it down so that you aren't. As long as the steam stays. As we go into describing detail. And then this is the, up here, this is the big crane that's used to move bundles back and forth between a gasket that's set up so that this is all flooded so fuel back and forth without getting it out of. The reason the fuel sits in the pool, that pool runs about 40 feet deep or so. There's actually two reasons in that kind of a pool. When it first comes out of the core, it's still actually very radioactive and very temperature hot because it's got this stuff called decay heat that you've heard a lot about as a part of this accident. And for about 5 years after, it's a lot of water to keep it cool enough. You can't immediately put it into dry casks. Hot. It's also very radioactive. Has anybody here seen a spent fuel pool? It's called Cherenkov radiation, and it's a really gorgeous blue glow, and you can actually tell by how much it glows. You can stand right on, and I have done that. I've stood at the top of a couple of different reactor pools, but there's no radiation going on. Water between you and the to shield you from any radiation from that pool. Why they're so deep is they're both keeping it cool and shielding the people on the floor that might be walking around. I understand why some of the issues with the water in the pools getting down wasn't just the heat, also the fact that they were losing. It suddenly became a problem in that you started to get radiation on top of that pool because that big, to help you understand what you're that's all about right there. And then this pool over here is the one where they stick the you stick it in there and it's so that's, I hope that now helps you then when we start to talk about this event, you've got a little bit better sense of what you're looking at because they're words on a piece of paper. What's really happening in that event. So that's it for me.
Thank you very much. Next we have Mr. Yamachika from Japan.
Guys are distinguished to have this opportunity. Fukushima event is the topic. My material is more than 50 pages. We will look at the other pages I skipped. And this is our organization. J. In Japan, the agency is responsible for safety regulation of nuclear facilities in commercial use. JNES, as a technical support organization, supports regulatory the technical viewpoints. The main of power plants and nuclear facilities, the analysis of at nuclear power plants. The third is the research. So this is the picture of the tsunami. Tohoku Pacific, which took place 40 days in Japan time of March 11th. The epicenter is of the Japanese islands. And east coast of northern